Well, friends, I have started talking about imperial smelting process, which is not exactly a modification of the lead blast furnace, although it is similar. It is much more than a modified version, because it has an attachment, a vital attachment for recovery of zinc, which come out from the top as zinc vapors. You understand this now, that whereas the lead blast furnace is designed to take only the product of roasting of lead sulfide concentrates, that is done in a sintering machine which produces lead oxide, lead sulphate. But this furnace is designed to take a mixture of oxides of lead and zinc, which come out of roasting, sintering of zinc sulphide, lead sulphide combination. So, from the ore which has both the sulphides, we get them as a concentrate where both the sulphides are floated together. There is no attempt to separate them. The only attempt is to recover as much as possible of the sulphides that are present. Then they will be calcined and roasted to produce the charge necessary for the imperial smelting furnace. In this also they have to be, we have to have granular material, it cannot be very fine. Now, yes. I have also mentioned that in this case the furnace is square cross section, operates at about 1000 degrees, more or less similar to the lead blast furnace operation, which operates at 1200 degrees. I did mention why it is called imperial smelting furnace. You should guess the very word imperial should tell us that it was developed in England. So, it has come from United Kingdom, that is why they have named it as imperial smelting. Now, the trickiest part of this entire operation is condensation of the zinc vapor, which is based on a very simple principle of physical metallurgy, the phase diagram of lead and zinc. Now, here is the phase diagram of lead and zinc. This you should understand. Lead has a melting point of 327 degrees, zinc has a melting point of 419. If you go to these temperatures, two liquids separate out. If you are at a temperature below 327 degrees, then you have lead and zinc in a solid solution. If we exceed 327 degrees, then lead will melt out. So, here you will have liquid lead and zinc. Zinc will be solid, lead will separate out as a liquid. If we go beyond 419, then we begin to get two liquids. One liquid is very rich in zinc, the other liquid is very rich in lead. If we go to a temperature like this, we will have a liquid which is richer in zinc, we will have a liquid richer in lead, and this actually comes down. But if we are somewhere here just above the melting point of zinc, there is very little zinc, very little lead in that what is separated out, and there is some amount of zinc which is in the other liquid. So, here we get two liquids, this liquid and that liquid. Okay. Their relative proportion will depend on the lever rule, where we are and where you are standing. If you are standing here, if this is the in the phase diagram, if this is the composition, then you will have this composition and that composition, and the ratios will be inversely proportional, how much of what will be there. This is made use of in the zinc vapor condensation. The principle is this: the vapors are coming out of top, and these are the condensation chambers. This is condensation chamber is shown in a magnified version. The furnace gases which contain about 6% zinc vapors, the rest will be CO2. As they come here, they are splashed by lead liquid at a temperature of around 450 degrees. So, liquid lead is splashed onto the zinc vapor, and that bath now has that zinc vapor in solution. Because if you go back to the temperature 500 degrees, 450 or so, if you refer to this thing, you will find now the lead can dissolve so much of zinc. So, what happens is exit gases will have very little zinc in them, only 0.24%, and rest will be CO2, but most of the zinc vapors are condensed and taken into a lead bath. Now, this lead bath would contain 2 to 4% zinc according to the phase diagram there on the right hand side. Then it is cooled and it gets separated out, cooled only slightly. It will cool down from 500, 1000 degrees it is coming. Lead bath is at about 500 degrees. It is cooled to 450 degrees, and immediately two separate layers come out, liquid lead and the zinc layer as per the phase diagram. If you go back to the phase diagram, if you come down to about 450, which is slightly here, you are getting one liquid of this composition, another liquid of this composition. And so, two layers are coming, one zinc layer which is almost pure zinc, and a lead layer which has very little zinc. This lead is again pumped back. This lead will go back for splashing again. The lead that is recirculated contains 2.15 zinc, and the zinc rich alloy will come out here. So, this is what is happening. You are taking out lead with 2.4% zinc, bit of zinc separates out, some zinc is left behind, then it is recirculated. In that process, gradually you get a zinc rich alloy, and the lead is continuously recirculated. So, it goes to a zinc holding tank. It is all based on control of the temperature. Liquid lead splashed onto zinc vapors, it will dissolve zinc, then it will be cooled, it will give up zinc, it will remain liquid, it will be pumped back. This is the zinc recovery system of imperial smelting process. It is difficult because one has to pump a very heavy element like lead. So, it is a tricky proposition, and it is the liquid is being pumped at a temperatures of 450 degrees, 450 degrees is going, and the entire operation is switching between 450 and 560 or so. Okay. Now, during my discussions, you must have heard me say the word zinc recovery from lead slags, because even in the slag that comes out of the imperial smelting process, some zinc will come out. Lot of zinc will also come out of the lead blast furnace, and lead blast furnace slags normally contain 15 to 18% zinc, zinc in solution in lead slags. How do we recover that? Because it is there some kind of a silicate. Now, they do that, we employ a process called slag fuming process at about 1200 degrees centigrade. In water jacketed reactors, no refractory, but water jacketed for reasons I do not clearly understand, but if you have a water jacketed reactor and there is it is water cooled, then there is always a frozen crust, solid crust all around, which acts like the protective refractory. In that furnace, in the bath, you have to go to this temperature because you are treating slags, and melting points of slags are around that, little below. To that is added coal, injected coal and air. So, you are actually gasifying coal inside a slag phase. So, coal will form CO and CO2 on gasification. This CO reacts with ZNO in slag to form zinc vapors. So, it is a reduction reaction. There is zinc inside the slag as ZNO. Inside the slag phase itself, you inject carbon and oxygen, and these two react, coal rather, carbon as coal, these two react, gasify coal, the CO formed reduces zinc oxide, zinc vapors come out. This is an endothermic reaction, because all oxide reduction processes by CO are endothermic. So, it tends to cool the entire bath. The heat can be compensated like this. Above the bath, when zinc vapors come out, it reacts with the oxygen in the atmosphere, forms ZNO fumes, that is exothermic. Also, the CO that is coming out, it will form CO2 beyond as it comes out, or it can be combusted to form CO2, that is also exothermic, that will give heat to the bath. So, some heat is gained by oxidation of zinc and oxidation of CO. This is the fuming process by which you are recovering zinc from the slag essentially as zinc oxide fumes. Now, these fumes, zinc fumes and zinc oxide fumes are collected in bags. There are collection bags of zinc. If we can do that, we can recover nearly 90% of zinc from the slag, and then we will also improve recovery of lead about 98%. These zinc fumes that come, it will go to the zinc plant. To get zinc out of that, it will either go for pyrometallurgical processing or for hydrometallurgical processing. Now, here is a small sketch to show how with blowing time the process will proceed. This is blowing time, blowing of carbon and oxygen in slag, and this is percentage zinc in slag. Obviously, the percentage zinc in slag, which is shown here and here, will drop with time, because gradually zinc is going out of the slag phase. Whereas, fuming rate, the rate at which zinc is coming out which is shown on this side. Initially it would be high, but with blowing time gradually the fuming rate will drop because there is not enough zinc oxide left in the slag. So, typically we need in minutes say 120 to 140 minutes to come somewhere here, and about 180 minutes, about 3 hours of blowing of carbon and oxygen to recover most of the zinc oxide from the slag phase. That is where the fuming rate becomes very low. Now, beyond this, if you continue the blowing, your fuming rate actually it already has dropped, it will drop even further, and zinc in the slag has already dropped, and maybe it is not going to drop any further. So, somewhere here one has to draw a balance, and you have to let go small amount, very small amount of zinc in the slag. It is not worth trying to recover that. So, you are coming to a situation which we often call the state of diminishing return. Means if you go on trying more, the elemental advantage you get is not commensurate with the efforts you are putting in. So, somewhere it has to stop. So, this is called zinc fuming process, which has to be applied for slags out of lead blast furnace for recovery of zinc. Okay. I have talked about Debari process. Now, I would like to say few words on nickel. Now, you may wonder why I am discussing nickel now, because earlier I have referred to nickel as a metal which comes from oxide sources. The reason I am bringing in nickel at this stage again is because nickel is also obtained from sulfide ores, and there are many countries in this world which has sulfidic nickel deposits. So, we can say that both oxides and sulfide ores are available, and both of them need to be exploited. Why are we interested in nickel? Because nickel is a strategically important metal. You know, when we word strategic, you must know what it means. The word strategic has two implications. When we say this is of strategic need, it means in the long term perspective it is required, means you will need it for very long term to satisfy objectives even in the long term. It also means that it has military and defense applications, because military is of vital importance. So, many alloys would need nickel for defense, and also there are many industries which will continue to need nickel for a long time. So, nickel is of strategic importance. In India, like in many other countries, it is of strategic importance, but we import all our nickel. We do not produce nickel, excepting for small quantities which we are obtaining from secondary sources. Let me talk about them first. When I was working in RRL Bhubaneswar, an entrepreneur met me saying that I live in Kanpur and there is an explosives factory there. There are fertilizers factories, and many of them use catalysts in their operation, and many of these catalysts have nickel in them. Now, after they are used, they throw away those catalysts called waste catalysts, and there are small hills of these waste catalysts, and he went and found out they contain metals like nickel, copper, zinc in very good quantities, much more than ores available anywhere. So, he bought them. He said, I would like to get nickel out of this. So, we tried to help him to establish a process for recovery of nickel from waste catalysts. In many chemical processes, nickel is a very important catalyst. So, we have these waste catalysts in our country, and people have here and there found some ways of recovering nickel. There are also some waste materials available from abroad, maybe alloys, maybe chemicals, etc., which have nickel in them. The country buys them, and some companies try to process nickel from them. These are secondary nickel, we can call secondary nickel, but from ores available in the country, we do not have a industry, not even in a small scale industry, to produce nickel. Now, nickel is vitally needed as a strategic material because of its alloying properties. We may not use nickel as such, but nickel alloys are necessary in chemical processing because of their high strength properties, corrosion resistance. In space research, nuclear reactor engineering, etc., for many alloys we need nickel. There are more than 3000 commercial alloys for mechanical properties and corrosion resistance qualities of nickel. And of course, you know, there is a group of metals called monel metals. These comprise of nickel and copper mainly, with some other things of various proportions. There is in the market an alloy which looks like silver, it is called German silver. It is prepared by mixing zinc, copper and nickel, it is German silver. Of course, I have not mentioned use of nickel as catalysts in many chemicals, but the maximum use is in the form of alloys. So, for alloying, if it is an iron based alloy, we can use as ferroalloy. If it is not an iron based alloy, then we have to put it as nickel metal. For example, if you have to make German silver or you have to make a nickel copper alloy, we cannot use a ferroalloy, you have to have nickel in elemental form. Now, in the world, there are many places where the sulfide ores, average the mineral composition may be Ni2FeS4 or NiFe9S3, there could be other compositions, but like copper, zinc, lead sulfide, these sulfides are also mixed with some other sulfides, because sulfides, as I have been mentioning, are very good solvents. Now, here are some figures about world production of nickel ores. I do not know whether you can read them, but I will just read out one or two figures. In Europe, in 1960, 2.1 thousand tons of sulfide ores were mined. In 75, 5.0 thousand tons, means 5,000 tons of sulfide ores were mined. Oxide ores mined were 8.6, so oxide ores were more. But in a place in Africa, there are more sulfide ores, as there are not, and in 1990 75,000 tons of sulfide ores were mined. In Canada, huge deposits of sulfide, nickel sulfides, and some 340,000 tons of this sulfide ores were mined. In USA, they have oxide ores, no sulfide ores. It is only in Canada and also in that, and also in the form of C nodules also has sulfides, but in most countries these sulfide ores are not there. Canada is an exception, but the nickel is there in oxide form in many countries. And if you look at these figures, India has very small quantities of oxide in oxide form, and in the chromite overburden that we mentioned, it has been estimated that we have already taken out some 185,000 tons of nickel ores which are there. Now, how do we proceed for extraction of nickel from sulfide? Here is a flow sheet called nickel extraction Inco. This Inco is a very famous company which is based in Canada, and you can see they are processing the nickel ores like this. Because they are sulfides, the ores will be like copper sulfide, very low grade. In this an Inco ore, there is only 1.3% copper and 1.2% nickel, as low grade as that. They will be ground and there will be flotation. Tailings will lose a little bit of copper and nickel, but the bulk copper nickel concentrate will have 6% nickel and 7% copper. So, we get a bulk concentrate, we float both of them together. Then they separate copper concentrate and pyrrhotite concentrate. We will get a concentrate 30% copper and 1% nickel, and we will get a main nickel concentrate which will have 10% nickel, 2% copper. This becomes now the starting point. It will now undergo a pyrometallurgical processing, very much like copper sulfide processing, where we will go through a matte route, through a route that will involve sulfides. So, this nickel concentrate sulfides, which would have 10% nickel and 2% copper, will go for roasting, reverberative furnace smelting, just like in the case of copper. There will be slag discard, and this will now produce a matte. If somewhere there is a copper slag available, that can go in here, because we need in the matte copper also. So, nickel sulfide processing also involves a matte, which is a mixture of sulfides containing 20% nickel, 7% copper. It will undergo converting, like exactly like in the case of nickel. The slag will go back to the reverberative furnace. In converting, we will have matte 50% nickel, 25% copper. There is a slight difference here. In the case of copper converting, by converting a straightway, we are producing blister copper. In this case, we do not do that. We produce a product which goes for slow cooling, grinding and magnetic separation to finally get a low copper nickel sulfide and high copper nickel sulfide. So, two products they aim at basically to produce nickel sulfide. So, the matte processing will be to prepare, like in the case of copper matte smelting, we wanted to have white metal and then that will convert it to blister copper. No, here they have first produced the nickel. Then it will go to a different pyrometallurgical processing, as you say here, fluid based roasting, nickel oxide. It can be marketed as such, or it can be reduced to produce metallic liquid for the market. It can go for fluid based roasting to get nickel oxide. It can be reduced. This can be carbonylation, means nickel pellets and nickel powder, reduction smelting, electrolysis, electronickel, all these can possible. So, in the sulfide nickel sulfide processing, the aim will be different. The aim will be to go to a matte phase and not the metal directly. Then the sulfide will undergo a pyrometallurgical processing through the oxide route. Now, the oxide ores are much more abundant than the sulfidic ores. It should be sulfidic. And the oxidic ores are called nickeliferous laterites, means they are associated with iron oxide deposits, typically containing 1% nickel and 40 to 50% iron in overburden, means in the top layers. There can be more nickel in layers below, and typically this kind of a composition we can expect, where nickel is in solid solution with FeO. In India, this is there in chromite mines of Sukinda. Sukinda valley is in Orissa, it is full of chromite and lot of chromite mining takes place there. Now, during chromite mining, they take the top layer out and they keep it at one stage, and hoping that in future someday we will extract nickel out of that. So, when I was working in Bhubaneswar, they said that you must go and see the chromite overburden which has nickel, and we were interested in extracting nickel. So, I was taken there. I was standing on top of a hill, and then I asked some people, where is that chromite overburden where there is nickel? Then I was told that you are standing on top of that. So, there is a hill of that chromite overburden containing say around 0.7, 0.8% nickel, which is waiting for somebody to come and extract nickel. The rest of the place, after the top layer has come out, they are doing chromite mining, that is going on. But this nickel overburden containing overburden is simply waiting. What do we do with it? That in oxidic ores, nickel is associated with nickel laterites. Laterites are iron oxides. Now, to understand the behavior of these ores when heated, we can take help of differential thermal analysis, which I have explained once. Let me explain it once again. In differential thermal analysis, we have two small crucibles placed side by side as shown, and they are heated in a furnace. There are two temperatures, there are two thermocouples attached to them, measure the temperature difference between these. Now, the sample whose behavior we want to study during heating is kept in one. The other crucible contains a reference material like alumina, where nothing happens. Now, when we heat in a furnace, these crucibles placed in such a manner that in the beginning the temperature difference between them is 0, because they are both getting heated up. But if something happens in this crucible, either exothermic or endothermic, then the delta T will be registered either this way or that way, because if it is endothermic, temperature will be arrested here, this will go up. If it is exothermic, temperature will go up here, and it will go beyond this. Of course, this will not continue. When it is over, it will come back to the baseline again. This simple technique is used to understand the behavior of any ores and minerals during heating, and I will come back to this in a later lecture about behavior of sulfides when they are heated. But let us discuss how nickel laterites behave during heating. Here I show a typical DTA plot for a particular laterite. Ore composition is given here, 1.7 nickel, 2.5, 25% iron, 24% silica and 18% MgO. Now, as we heat this ore, the DTA analysis shows the following. The small endothermic peak at W, which is at about 100 degrees, is due to evolution of a small amount of water from an already dried sample. It has been dried, sun dried, there is some moisture still left. The ore from the mines contain lot of water, some as moisture, some in combined form. We have to remove that also. So, the first endothermic peak shows endothermic evolution of water, it absorbs water. Now, there is another big endothermic peak at G. What is that G? The second endothermic peak G at about 230 degrees is due to goethite decomposition, and goethite is 2FeO-OH. This phase is called goethite and it decomposes into Fe2O3 and H2O. So, goethite mineral, which is FeO-OH, it decomposes at about 230 degrees to give off Fe2O3 and combined water H2O. Now, this is a very important observation, because it has been found mineralogically that the nickel is actually always associated with the goethite phase. So, before this temperature, nickel is inside the goethite phase, almost dormant, but the moment that goethite decomposition takes place, nickel that was liberated with goethite was associated with goethite is now liberated. It becomes active, nickel oxide becomes active and it can be very easily reduced. Then we come to the third endothermic peak. This third endothermic peak refers, which is about 530 degrees, it refers to dehydration of serpentine. Now, serpentine is a mineral which is there in the ore. Its composition is magnesium 6, Si4O10, OH8. It is a very complicated mineral. This oxide in the serpentine becomes active above 600 degrees. The next exothermic peak, this is very critical. The serpentine phase crystallizes, that Sc at about here shows crystallization of serpentine. Now, the next exothermic peak Sc at around 800, which represents the recrystallization of the magnesium silicate, which is liberated from serpentine into olivine. It is Mg2SiO4. If this happens, then nickel oxide is locked up in that phase. The sum and substance is this: when you are heating a lateritic ore, water comes out, goethite decomposes, liberates NiO which was in the goethite, then the serpentine phase goes through decomposition and recrystallization. If that happens, then nickel oxide goes into that serpentine phase and becomes inactive again. It is not available for reduction. So, whatever we do will have to be done below 800 degrees. This is the sum and substance of that. So, we can say that in ores which are lateritic, everything has to be, all pyrometallurgical operations must be below 800 degrees to ensure that nickel is not locked up in a serpentine recrystallized phase. However, when there are limonitic iron ore which have more iron content 40 to 50% Fe, that would not have the serpentine peaks, but a serpentinic ore with a low iron content 8 to 10% Fe will not have the goethite dehydration peak of the lack of goethite mineral in the ore, hence does not have the peak of serpentine. So, there are some laterites which are easier to reduce than the serpentinic ores because of the olivine recrystallization and locking up of the nickel oxide in the olivine will not take place. What I am saying basically is, not all nickel ores are alike, and one has to first go through many laboratory tests, know what happens when we are heated, when is nickel oxide easily available for reduction, and unless those things are done, we simply cannot do a pyrometallurgical step. To understand now better what we will do for preferential nickel reduction, we have to go to see the simple phase diagram. Not phase diagram, that this diagram which shows the different phases at different tensions as a function of percentage CO gas. It is something very similar to what you may have learnt in iron oxide reduction. If we have temperatures in this range and CO in this range, then we should have a final product nickel and Fe3O4. If we maintain temperatures and CO2 composition in this range, we can produce nickel FeO, and of course, if you go to percentage CO higher than this in temperature ranges like this, you can produce both nickel as well as iron in elemental form. This is the kind of guidance we get from this diagram. You must have seen similar thing in the case of iron ore reduction. Now, one restriction we have put is in the ores, some ores where we have goethite, serpentine and all this, at least in Indian ores, we never go beyond 800 degrees, all operations will be on this side. Now, if we can reduce the lateritic ore which is nickel oxide initially locked up in the goethite phase and then liberated, then we can very easily produce nickel Fe3O4 or nickel and FeO. It is quite easy to do. Nickel oxide is very easy to reduce. What we depend will depend on the final processing. Now, by keeping controlled temperature and PCO, one can produce nickel and FeO if you want to leach out FeO, or you can leave nickel and FeO and Fe3O4. We cannot handle nickel and Fe2O3, that will not be desirable because Fe2O3 is difficult to reach. In smelting, reduction smelting, calcined ores are smelted in electric furnaces with 50 to 1650 degrees C. Now, there we do not have to worry about all this. Whatever we have, nickel oxide, Fe2O3, everything we can smelt at temperatures of 1550 to 1650 degrees. We reduce both nickel from the oxide as well as iron from the oxide, and we produce a ferronickel. And since we are using carbon as a reducing agent, if you give a long time, more nickel will come out, more iron will also come out. Nickel comes out earlier because it is very easy to reduce. So, initially we can produce a high nickel ferronickel, but total recovery of nickel will be low, because we need more time to take out all nickel. So, one has to draw a compromise between recovery of nickel and the grade of ferronickel, but we can take out both iron and nickel as ferronickel from the charge. Now, in pyrometallurgy we go a bit differently. We combine the initial reduction of the lateritic ores to such an extent that we produce nickel and FeO, Fe3O4, and that nickel can go for ammoniacal leaching. So, that charge which has been reduced under controlled atmosphere, and there are furnaces. One is that rotating hearth furnace, or it can be in a rotary kiln, that can now be sent for ammonia leaching. Nickel can be easily leached by ammonia to produce nickel amine, from which we can precipitate nickel carbonate, and nickel carbonate has an easy market, because nickel carbonate, if it is added anywhere, it will easily decompose and produce metallic nickel. So, from these oxidic ores one can produce ferronickel, one can produce metallic nickel. For that we have to go for electrolysis by decomposing nickel carbonate into nickel oxide, dissolving in an acid solution, electrolysis. It may not be necessary. If it is for alloying, if you add nickel carbonate, it will decompose very easily. So, what we want is we have to keep in mind what it is what we want. If you want ferronickel, we have to go for smelting, but we can also produce elemental nickel by initial this reduction roasting followed by leaching of nickel. Now, this sort of work has been done in India, and I will in the next lecture come back to this subject and give you little more data and discuss it more thoroughly. Now, let me end today's lecture by discussing a subject which might become important in the future. See, so far what we have done is that we have talked about sulfides undergoing a flotation process. We can either get a copper fraction which goes for copper extraction, or we take zinc sulfide concentrate goes for zinc, or lead sulfide goes for lead extraction, or copper, lead and zinc together which goes for imperial smelting process. But there are quite a few sulfide deposits which are known as multi-metal deposits or mixed sulfide deposits, which are not very easily amenable for differential flotation to get rich concentrate of this or that or the third metal. They may be very low grade also. Now, these mixed sulfide deposits are drawing attention in India, because India is not very rich in terms of the deposits of copper, zinc and lead. How do we proceed to treat complex sulfides of lead, copper and zinc? Now, here are some simple some hints, but this I may discuss later on. First of all, we need to find concentration techniques. Flotation is one. We can also employ gravity separation to separate large extent zinc, lead, copper all together. Differential flotation is something we employ on sulfide minerals. Total recovery of all the sulfides or fraction, this fraction separately. But for this we need that the minerals are present as discrete minerals. Suppose we want to separate copper, lead and zinc, the minerals must be discrete. Zinc sphalerite, galena, copper pyrites, if they exist as distinct minerals, then differential flotation is possible. But very often they are not distinct minerals, they are all mixed together. Like in copper pyrites, you have Cu2s and Fes not as a solid solution, it is a separate mineral CuFes2. There can be such minerals which combine these elements. If that is there, then by flotation you cannot get different fractions. If we do a retort distillation, we can separate zinc, like in the retort process for zinc. If you take a calcine which has both lead and zinc, like in the imperial smelting process, zinc can be separated out, lead, copper will be left in the gangue, and the zinc finally obtained contains some lead, there will be some lead. We can think of electrolysis to produce zinc from a leach liquor containing lead and copper in addition to zinc. Now, this I will discuss, I have to think. One can apply liquation to produce molten lead zinc bath containing 1.2% lead and lead containing 0.5% zinc, something that we have employed in imperial smelting process. So, many things have been thought of as to how you handle a mixed sulfide, but ultimately people think that when you have a sulfide deposit, all kinds of sulfides, the best way to go will be to employ a hydrometallurgical technique. And here the aim will be, of course, the technique will have to be depend on the gangue minerals and the percentage compositions of various non-ferrous metals present in the ore and the bulk concentrates. It will always depend on that. But the first major step in hydrometallurgical method will be absorption of non-ferrous metallic values in solution and leaving behind a major part of iron in the leach residue. Iron is the part in the sulfides is not what we want. So, if there is a bulk sulfide concentrate, we have to find a way to take all the metals in the solution, copper, zinc, lead and others, but not iron in the solution. Iron must be rejected. That if we can do that, we have a very good starting point. Then the next steps would be solution purification, separation of non-ferrous metals from each other by cementation, precipitation, solvent extraction or electrolysis. Fluidized bed roasting helps in selective conversion of non-ferrous metals in the ores and concentrate to sulfates. If you have fluidized bed roasting where PSO2 and PO2 are controlled, then from the calcine selectively we can get sulfates and oxides, and sulfates can be of a particular metal can go dissolve in water and taken out and things like that. So, this after fluosolid roasting we can have solubles in dilute acid or water, and that will give us some separation, etc. Many other things are possible. Right now, we are not doing that. Mainly the industry is working on concentrates which are very rich in copper pyrites and CuFes2 goes for copper extraction, and on concentrates which have zinc and lead. If they are separated by flotation, then it goes for zinc extraction, lead extraction separately. If they are floated together, it goes for imperial smelting process. This is the state of affairs in our country, but very soon we will have to deal with some deposits where we have to do something for when there are all the three metals present there. We have to find how effectively we can extract them and separate them. I will discuss that some other time. Thank you.